We need two things for this to be a probability distribution. We need the individual probabilities to be between 0 and 1, fraction decimal, and we need the sum of all the probabilities to equal 1. And it works well set up a table for this with all the possible outcomes, and then you figure out the probabilities so that you ensure that your sum is equal to 1. Now, the sheet that I gave you is in all the triads. I got it. Thank you. That's already better. More. Okay, so now we want to verify that this, in fact, in example 3, on page 175, we want to verify that this, in fact, is a probability distribution. Each probability has to be between 0 and 1, and the sum of all probabilities has to equal 1. These are the only two rules that we need. So we take a look at these guys, and we say, yes, each one of these is between 0 and 1. That meets the first criteria. Then we sum them up. And when you sum them up, it does equal 1.
Oh, I thought the 6 was on the, it was 0.6.
0.06. It does equal 1. So it matched both of these criteria. So we know that this is a probability distribution. And remember what I said yesterday about the 0? The 0 is tricky. Yesterday in the list they gave us, they didn't have a code for 0. They did 1 through 5 for the passive aggressive. But if they're giving things like how many things were taken, how many days are, 0 could very well be a possibility. So before you start your chart, make sure that 0 is valid or not. Okay, so now, the Try It Yourself 3 says, take a look at the one we constructed, this sheet. Does this meet all the criteria for your probability distribution? Is the probability between 0 and 1? Mara says yes. And the sum of all probabilities is what, Courtney? The sum of all your probabilities is what? 1. Very good. Sum of all your probabilities.
Oh, it's getting worse. It's just getting worse.
It certainly works now.
Oh, yeah. Now everyone's looking at me. My phone didn't even ring.
No. You're ratting her out for sure.
Oh,
okay.
Yeah.
Now, when we did this chart yesterday, all these possibilities we wrote down. So when we calculated your total frequency and we do part over whole, this is gonna work out. That's why you do this probability distribution. Okay. Any questions on that part? All right, let's take a look at another one. All right, you're going to decide whether these are a probability distribution or not. Now, it can go vertical or it can go horizontal.
Hey, Victoria. Guys,
Okay, so what do you think about the first one? Does it meet the first criteria? Does each probability fall between 0 and 1? Yes. So the probabilities are between 0 and 1. Is the sum of all probabilities equal to 1? Add them up.
No.
No. The sum is equal to 1.07. So therefore, no. This is not a probability distribution. Only two criteria, guys. The probabilities have to be between 0 and 1, and the sum has to equal to 1. This is not binomial probabilities. This is just any probability distribution. How about the second choice? What stands out?
No. Because
it's not between 0 and 1, and we also have a negative.
There's no negative probability.
There's no negative probabilities, absolutely.
Yeah,
okay.
Thank you, Gunner.
So now, you guys take a minute and decide these. Now, in number 1, just because the fractions are different doesn't mean that they're not going to add up to 1. If you don't have a calculator handy, convert your fractions to a common denominator.
That's a lot of work.
Yeah? Not really.
I got it.
What'd you get?
I got no reason why.
Reason why?
Because multiply 5/8 times 2, you get 10/16. That's surplus 11/16. If you multiply 1/4 by 4, that's 4/16.
4/16.
And
Good.
then that'll be like 15/16. And then the other 3, that's like 16 with the remainder 2.
Good. So it's over. So Darian says this is over 16 over 16, which is 1. Good. It was over.
It was actually 18 over 16. So that's
Okay. Good. So that one's not a probability distribution. How about the next one?
Yes.
It's yes?
Yes. They all add up to 1.
Okay. Joe said they add all up to 1,
Nah.
and they're all between 0 and 1.
Yeah.
The only criteria, guys, 2 pieces of criteria. They have to be between 0 and 1, and they have to sum up to 1. That's the only 2 criteria that we get from this. Now, we're going to take a look at your mean, your variance, and your standard deviation. You get a couple of choices here. There's another column on your table that will help us calculate the mean. We can still use your calculator and use L1, L2, and get the X bar, the mean from that.
Wow.
Remember, January 1st, this changes, guys. This totally changes with lateness. Okay, well, January, whenever you come back, it changes.
Oh.
6. Okay, 6. Wow.
Right.
Wow.
This is more tomorrow, so I say you see you 2013.
Great. We'll see you till next year.
Are you good class?
No.
I am. Okay.
All right. All right, now. God bless. Guys. Okay, now, we can find your mean by taking the sum of this column right here. There's the third column, there's the third column on there, actually the fourth column. X times P of X. We take the X value times the probability of that value. We take all the parts to it, and when we add them up, this is the same as our mean. It doesn't mean that you can't go into your table and do L1, L2. Now, in your table, the nice part about this, let me move this down a little bit. There's a couple of different ways to do this. In your table, what happens when you do this times this, these two, when you do this times this, what your calculator sees is if this is L1 and this is L2, remember, it multiplies each one of these, gets that, and then it adds it all up. And it divides by, in your calculator, it will divide by the sum of all your frequencies to give you your mean. These are 2 tables. Say you did this. I had a 0. I had 4 occurrences. A 1. I had 8 occurrences. A 2. I had 3 occurrences. It multiplies these. So 0, 8, 6. It adds this up. So it adds these all up. It adds these pieces up. And then it divides by your total over here. Now, what happens in your calculator is if it adds this whole thing up, and these are all your probabilities add up to 1. So it divides by 1, which is the same as saying just multiply and add them all up. Because in your calculator, it will just divide by 1. So essentially, your calculator is doing the same thing as this one does, because this total is 1. So it has no effect when you put that in. If you put it in opposite and you put your frequencies like the original 2 tables, L1, L2, it does the exact same thing. It adds up all your frequencies after it multiplies, and it divides through that. So either way, you're going to get your mean. So we're going to walk through doing this on this chart, but in the future, you can do your L1, L2. Kind of like we did the standard deviations. Remember we walked through that big terrible looking standard deviation
Oh,
table?
I hate that. I didn't
But it's a good thing to do because you need to see where your standard deviations come from. Once we get through the table, then you can use your calculator to get through all your parts.
You learn the
So,
basics.
what this is saying is we've already determined your probability. Take your x value times your probability and then add them all up. This right here is the mean for your data. To find the standard deviation, you're going to go to your L1, L2 anyway. So we're going to have to revert to our table. They give you a formula, but we really don't use their formula. But we'll walk through this. This is your table. We just did this. This is your try it too. This is the one we did yesterday. So we figured out this all added up to 100. This is what we did yesterday. So we divided 16 divided by 100. And when we divide everything by 100, we just need to move the decimal place 2 places. Watch the 9. You got to move it and put a 0 in front. So if I add all this up, what should this equal? 1. So we know this is a probability distribution. Each probability is between 0 and 1, and the sum is 1. Now, when you multiply these, you're going to multiply, this is your x column, times this, and it's going to give you this. We're going to do this 2 ways. We're going to multiply it out, then we're going to put it in your table L1, L2 over here. Then we're going to put it in your table L1, L2 over here. And we're going to see if we get the same mean and the same standard deviation. Okay? This way we know, can we use our table for this or not? So let's go ahead and multiply these guys across. You're going to multiply across, you're going to have to add these down. When you take the sum of this, this will give you the mean. So let's add them all down. Oh, let's take the sum and add them across. Let me get my sheet out. So we're multiplying across.
Do we have to like count decimal places if we do it or not?
Oh, you definitely, let your calculator multiply. Oops, I'm off. I don't know. I'm off here. It's 63. I think I missed this one. It's 36. Okay, when we add this all up, this will give you your mean. Now, what this tells me is this. These were our sales per day, right? Am I off on something else?
You missed something like 3 times 20.
3 times 20, oh, 63. It got cut. I erased part of it. Sorry about that. Okay. We were calculating out of 100 days for one person how many sales on the average they made per day. Right? God bless you. So we said they can make anywhere from 0 to 7 sales in a day. And this was the frequency that they did this. So out of 100 days, 8 days they made 6 sales. 10 days they made 5 sales. God bless you. 16 days they didn't make any sales. Okay, now, when we come up with the mean, the average, that means on the average, this person makes about 2.6 sales per day. Now, sales is what kind of number? Discrete or continuous?
Discrete.
Discrete, because you really can't make a half a sale. We're going to count them as a whole or not done yet. But remember, when you take an average, you always go 1 decimal place more than your x value. So there's no x value in, no decimal, sorry. There's no decimal place here in your x values. So our mean is 1 decimal place more. So on the average, this guy makes about 2.6 sales per day. Now, let's have this half of the room do L1, L2. Okay? Let's have this half of the room do L1, L2 over here. And see if we come out with the same mean and the same standard deviations. So, for this group over here, what's your mean?
2.6.
What is your population standard deviation?
1.93.
Okay, what is your sample standard deviation?
1.94.
Okay, thank you. This group over here, Tamara, what's your mean? Okay, what's your population standard deviation? Okay. Anybody else get when you get your mean, your population?
I don't know if I did it right, but I got 1.928.
1.93, okay. And what's your sample standard deviation?
It's blank.
It's blank. Okay, it's blank. Now,
Is it something? Is this supposed to be like that?
no, it's absolutely supposed to be like that.
Oh.
Okay, now, I need your attention up here so you understand the difference. Both of these means are the exact same, right? The means are fine. We can understand that the calculator, how it calculates a mean. We know it's multiplying, we know it's adding it, dividing by what it is. Both ways, it will be fine. If you add all these up, you divide it by 100. If you add all these up, you divide it by 1. And when you calculate your mean. So both ways, your mean is okay. Here's what happens with your standard deviations. These guys, your populations, are going to be the exact same. What happens with the sample standard deviation, if you remember back to the original table that we did for standard deviation, we came down, we took the difference of the squares, the sum, and we divided by n. This gave us our population underneath your square root. When we did a sample, we divided by n minus 1 to do the sample. We said for a sample, it makes it a little bit more leeway for it. Gives it a little bit larger standard deviation. Not a lot, but a little bit. Now, what happens in this, if your total is 1, your calculator cannot do 1 minus 1. It cannot divide by 0. So therefore, it doesn't give you a sample standard deviation. The only standard deviation you get is your population standard deviation, which you would have to use for either sample or population. Do you see why this one's not giving us one? Because in your standard deviation, you're going to do n minus 1. So therefore, if I subtract 1 minus 1, I cannot divide by 0. So we're going to determine that even though we can build this table ourselves, we can absolutely go to our calculator to get our results that we need. Does it make sense? Okay? Now, from here also, you can take this and you can make your probability distribution. Your probability distribution is a graph. And in this case, it would be like your relative frequency graph. So if I'm looking at these guys right here, guys, I need your attention. And we want to make a probability distribution. We're going to do this the same way that we did your relative frequency graph. We're going to put all your x values down here. 0, 1, 2, 3, 4, 5, 6, 7. And we're going to put your other pieces from 0 to, we don't have to go too high on this, like 30, so we can go by 0.05s. When you label again, make sure you think money, or you're going to get your labels wrong. Think money, like cents. When you do this part, don't label at 0.5. 0.5 and 0.05 are two different things.
Oh, yeah.
So think like money,
Think
5
money.
cents. Yeah, 10 cents. Think money. Now, to do this, this is the same as your relative frequency graph. For 0, we're at 0.16. For 1, we're at 0.19. For 2, we're at 0.15. And for 3, 0.21. For 4, we're at 0.09. For 5, 0.10. 0.08, and 0.02. And we would label. These are sales per day. This is our probability of X. Where we called it a relative frequency, we'll just call it your probability of X. And these are your sales, give it a title. Right? So this bar chart, this frequency chart, looks very much like your relative frequency, because relative frequency is part over whole, probability is part over whole. So we can do the same exact graph for this. And sometimes it's nicer to look at a graph. You could see where they make more sales. Here it's higher over here. If you remember, the average is 2.6. So it kind of falls in over here somewhere. See your tail? Kind of follows your tail here. The mean is pulled a little bit to follow that tail. Remember when we did the skewing? It's skewed right a little bit. Most of your data is sitting right here. Probably not the best for a salesperson. You probably want your data to sit on this side. You do more sales per day. But he's got a little bit less sales per day, and he's averaging 2.6, somewhere right in here. That's where his average is. When you look at a chart, a graph, sometimes it just makes a little bit more sense, right? Makes a little bit more sense?
Yes.
Okay.
Visuals.
Yes, it's totally visual. Okay. All right. And the last thing we have is expected value. Expected value, and this comes into play with your lottery tickets and all of that. We did your standard deviation, so I'm not going to do that. The expected value is, what do you expect to happen over a period of time? When we take a look at expected value, it's basically, what does this cost me? What do I get back in the long run? Like if you buy a lottery ticket every week, you might end up paying more than you get back when you finally win. So you want to figure out what your expected value is going to be. And in probability, we do a lot of expected value. We do a kind of a really just like, we really like use your mean for this. We kind of figure out what you expect to get back. But again, we're looking at exactly what your mean is in your calculator. You can put it in your L1, L2 just as easily. So let's take a look at this example. This field in itself, if you go into statistics, expected value is a very major part of statistics. We hit like this little tip of the iceberg in expected value. But if you're going to be a statistician, expected value is one of your major topics. So, at a raffle, there are 1,500 tickets that are sold at $2 each, and there are 4 prizes. 1,500 tickets, and there are only 4 prizes. The 500, 200, 150, 75. You buy 1 ticket. What is the expected value of your game? Now, when we do expected value, we take a look at the X, what each ticket is worth. Here's your tickets. You've already paid out $2, so we take out the $2 out of that, because you paid your $2 out. And these are your possible winnings. This is your loss. You've lost $2, you didn't win anything. So your expected value out of 1,500 tickets, there's one of these, one of these, one of these, one of these, 4 winners, and everybody else is a loser. Right? You only got 4 winners out of all of this. And I don't know if you heard the way they did the new lottery. They increased the numbers from 0 to like 70. Your choices to select numbers. I was listening to the news the other day. It used to be, I forget, like 230 million to 1. Now it's like $500 million to 1 for your chance to win. They decreased the Powerball part, like what numbers they have available for that, but they increased from like 40 to 70 on the possible numbers you could select. So to win a mega lottery thing now, your chances are much, much less. Yes.
The lottery, my dad's friend had 3 numbers in the Powerball, and he thought he won like a couple $1,000. He got $50.
$50.
Yeah.
Wow.
And he had 3 numbers in the Powerball.
And the Powerball, that's pretty bad. That's pretty bad. You would think. So now, when we do this, we're saying here's your x times your p of x. We're going to multiply these out. I thought I had this already multiplied, but I don't. We're going to multiply this out. And if you take a look at your book, they multiplied it. We're just taking this times this, this times this, this times this, and then they're adding them up. And technically, what you get is your mean. So you can do this the same exact way you do this in your calculator. L1, L2. And you can put it in your calculator. But remember, when you do your one-var stat, you have to say L1, L2, or it'll only take the L1 part. So they multiplied all of these, and that part's in your book. They added them all up after they multiplied, and they got negative 1.35. Now, because the expected value is negative, are you gaining or losing over time? Losing. So you can expect to lose an average of $1.35 each time you buy a ticket. It kind of takes into account, should you ever win one of these out of 1,500 tickets. In other words, if you did this for 1,500 times, your expected value over time is you're going to lose money on this particular raffle. Because their prizes weren't that great. If you think about it, if you bought your tickets for $2 each, and there's 1,500 possible winners, you're spending far more than you're getting out of this. Yes.
Yeah, what are they gonna do with the other like $2,500?
Well, when someone gives a raffle, they do it to raise money. So their goal is to raise money, not to collect your money and give it back out. Your goal is to raise money, but you offer a small prize to those that are donating.
I wouldn't do that.
Well, yes, but that's what companies do, especially, when they're trying to do if you ever been to a fundraiser, like even 50-50s. What about a 50-50? When you buy a 50-50, you only get half of the prize money. Where does the other half go? To the fundraiser. That's the goal of doing that.
Yeah, but I was weird. I was donating money. I mean, like, I understand if you could donate money for, like,